Hello everyone, good afternoon. Welcome to the class ECE317 Digital Signal Processing. Today we will consider the sampling problem. We just finished the midterm exam, right? Now we will start a new chapter. That is sampling theory. Let's go to ECE317. This is for the 9th week Friday's class. All right. So the sampling process. In time domain, this is a very simple thing. You suppose you have a XC of t. This is a continuous time signal, analog signal. And this is continuous time signal. Put C here means continuous, and the variable inside it should be t. T is the time. T runs from negative infinite to positive infinite continuously. So for any time, you have a value. Right? This is a continuous time signal. Then you take sample. Every time period, every t as step. At a step. Then you have x of n, which is a xc at n times capital T. Now n drawn from the n should be integers, so 0 or negative positive 1, negative positive 2, and so on. Okay. So the sampling process just looks like this. You take samples, like for example, you have a signal, then every t, 2t, 3t, you take a value, and you take value. This side you have more, right? You take values, and then you have x of n. Here should be n. This one is t, xc of t, and this is n. Then you have those values for every n equal to 1, 2, 3. This side is negative 1, negative 2, and so on. Here's x of n. Then of course there are something different. If you use small t or larger t, then the sample will look different. For example, if you double the t, you will have these as samples. Then you will have, okay, this value is same, and second will be here, and the third one will be here, right? And this one will be this one, right? Like this one value. This is 1, 2, negative 1, and another sample signal for t, for larger t, right? Things like that. Yeah. Okay. Then we have a basic problem. Actually, two problems. You can say two problems. I also see one problem. The problem is when you have these sample data, can you recover the original signal? You can also think the problem like this way. Do you have all the information of the original signal by these samples? Of course, you lost something, right? Like between any two samples, when you only have samples, you do not know the value between them, right? You do not know the values between them. So maybe the curve here will be like this way, maybe like this way. You do not know. You only know these two values, right? So you lost something. Then you will think, if you have more samples, now of course you will have more information of the original signal. If you have less samples, you will have less information from unregional signal. So here you have to choose how many samples will be a good choice when you take samples, right? We say that every second, how many samples do you want? You will think like you take more samples, then you have more information, but you need to save more samples, right? You have less samples, you do not need a lot of space to store to save the data, but you lost more information from original signal. Yeah. So the thing is that you have to find the balance. The balance is you lost some information, but you think it's fine. And another side is you have enough information, and you won't cost you too many space to save this data. All right. Then we use the Fourier transform. Use Fourier transform. Fourier transform provide us a very powerful tool. And here for this one, we can use Fourier transform. When you look at the signal in the frequency domain, we will see we can have more information to help us to make a decision how to choose the samples, how many samples you want to have. Yeah. This is you can say is a very beautiful application of the Fourier transform. The formula just look like this. Of course we need to know the continuous times Fourier transform as well as discrete time Fourier transform. So I list them here. The continuous time Fourier transform, CTFT. For signal g of t, it is defined as capital G of, we use the notation J capital omega. Well, omega is just for frequency. I use capital omega, that means this is for a continuous time signal. Alright. This one equal to integral from negative to positive infinite, then g of t times e to the negative j capital omega t dt. This is a CTFT. And we also have inverse CTFT. So suppose this capital G is given, then we can determine what is a lowercase g. Right. We have the formula is like this. G of t is 1 over 2 pi integral from negative infinite to positive infinite. Then this capital G times e to the positive j omega t d omega. Right. So this is CTFT. Now we can compare with the DTFT. We should be familiar with this, right? DTFT, we start from a signal x of n. Now the time variable is n, only integers. Its value only integers, right? Then we have capital X of e to the j omega. Now for discrete time signal, I use lowercase omega for the frequency. Yeah, both are frequency, but when you say, okay, g of, here's a capital omega here, that means this is a Fourier transform of a continuous time signal. When you say omega is a lowercase omega, then the time domain is a discrete time signal. This one is defined as a summation of x of n e to the negative j omega n, and n run from negative to positive infinity. Actually, the meaning of these two are same, right? You have integral here. Here is a summation. Summation for n run from negative to positive infinity. Here is the integral for t from negative to positive infinity. And the only thing is that this t is continuously and this n is discrete time. Then the signal itself. Then the power e to the negative j omega t, e to the negative j omega n. N is also time, right? N is also time. Okay. Then the inverse is also similar. This is this is inverse. I'm sorry, I lost that. This is a DTFT with inverse, and this is a DTFT, right? Two direction. This is DTFT. This is inverse. By the inverse, it is we can find the original time domain signal based on the frequency domain. This spectrum we call it. This is also 1 over 2 pi, but the integral from, we can pick one period, like from negative pi to pi. Now you can also use 0 to 2 pi, one cycle of the angle. Right? Here will be capital X of e to the j omega, then e to the j omega t d omega. Yeah, so these two formulas, these two inverse Fourier transform formulas, almost the same. Only thing is, here's from negative to positive pi. Here's a negative to positive infinity. All right. Now we try to apply to U them, and by some works kind of math, we have the following result. Here we have two signals, right? One is xc of t. Take example, we have xn, right? Then this one we perform xc of t. We perform the ct of t. We have capital XC of j omega, and we take sample. By sampling process, we have xn. I put t here. T is a sample, is a step. Every capital T you take some, right? Sample step. Then x of n, we perform dt of t. We will have capital X of e to the j omega. Then these two, they are related. How to relate it? We have this. This one, the dTft of x of n, is 1 over t summation of capital XC of j omega minus 2k pi over t. K run from negative to positive infinity. Is this one. That means if you know capital XC, then you can have capital X of e to the j omega. You base on this formula. Alright. Then let's look at inside this formula. What is the meaning of this formula? You can see omega minus 2k pi. This is what? This is a shift to 2k pi, right? You do a shift. You shift the signal 2k pi to 2k pi, shifted by 2k pi. And omega something over t. This one according to what? You have a scaling by t. When omega equal to t, xc of j omega over t equal to xc of j times 1. Right. So the thing is the value of xc at 1 were equal to the value of capital X at omega at t. Omega equal to t. Right. This is a scale. This is scale. Okay. Okay. If we use graph to represent it, things like that. If this is f of t, this is f of t, then f of t minus 2k pi, it will be, here's 2k pi. Right. Here's 0, here's 2k pi, shifted to 2k pi. When t equal to 2k pi, you plug in here, you get f of 0. F of 0 is this point. Right. So when t is 2k pi here, this value will be same with this value. And then the shift I show you this one. Suppose this is a ft. Then, like here's some alpha. Then this one will be, this is f t over t. It looks like this. This point, t equal to alpha t. You got it? You just extend this, extended by a t, When t is alpha t, you plug in here, you get f t over t. When t equal to alpha t, this gives you f alpha. Right? F alpha is here. So this is a scale. Right? This is scaling. This is a shift. This is the case t larger than 1. Right? T larger than 1. If t is smaller than 1, then this will be a narrow. Right? You push it, not extend. You will press it to make it less smaller. Right? Okay. This is a case t larger than 1. It's like this. So now you look at it here. Here we have both. We have scale by t. We also have shift by 2k pi. Shift by 2k pi and scale by t. So you can see like this. If xc of j omega looks like this, just like this one, for example. If this is xc, here's a capital omega, like this. Then here's the infinite terms. We just look at one term. That one term, it is xc of j times omega minus 2k pi over t. This one will be now shifted to 2k pi. It looks like this. Here's 2k pi. The center now is 2k pi. Here center is 0, right? So it shifted to 2k pi. And also, if this one is alpha, this is alpha, then this point will be 2k pi plus alpha times t. I suppose t is larger 1. This is the case like this. If t is smaller than 1, or like this point is also 2k pi plus alpha t if t is smaller than 1. Right? So two cases depending on the value of t. If x looks like this, then this one will be this one or this one. Now this x contain infinite this kind of things. Each center at 2k pi. Now can you imagine what it is? So every 2k pi you have things look like this. Every 2k pi you have this, and you do a summation. Alright, we can use an example to see. We consider a signal. Consider xc of t, which is some. Okay, I use e to the negative t times u of t. Okay, this one you take the CTFT, continuous time Fourier transform. You can have the result from Fourier transform tables. The continuous time signal, you do Fourier transform, you also have tables. This is one term in the table. You just check online, you can find that tables. And we have, we know capital XC, J omega. This one will be 1 over A plus J omega. Not A, here's A is 1, sorry. 1. Just 1 plus j omega. 1 plus j omega. Alright. If here's a, negative at, then here will be a. Now it's 1. Now it's 1. So we have this. You check table, search online, you can find it. Then we take sample. Take samples from XC of t with step t. With step t. You can choose different t. You can choose different t. Now I just put t. We have x of n, which is xc of n times t. Then I plug in, this is e to the negative, now time is n capital T times u of n capital T. So this is, I can write it as e to the negative t to the power n. And this is just u of n. Right? Same, u of n. For positive n, this is 1. For negative n, this is 0. For n 0, this is also 1. Right? So it's just u of n. The next one, now perform DTFT. We have capital X e to the j omega. There will be what? There will be, we still use table. We have this table. This is 1 plus no, not 1 plus, should be this will be what? This will be 1 minus e to the negative t, e to the negative j omega. Right? We have this one. We have this one. Okay. Try to compare these two. Try to compare these two. How do they look like? How do they look like? Yeah, you can calculate it by computer. If you want to work by hand, you can see, you try different omega value, you plug in, then you have this value. Different omega value, you can have this value. You can have the graph. And here we can use computer to do this thing. I open it here. MATLAB. Okay. XC, this one. Okay. Omega. Okay, omega equal to, we choose omega like a negative 10 to positive 10. Can we? Yeah, we can choose any omega with a step, step 0.02. Alright, so that's enough, right? So we have some value of omega. And the first one, we want capital XC, that is 1. Okay, I just want plot the graph. This is figure, first one, figure 1. Figure 1, I plot x-axis is just omega, and that y-axis is just that 1 over, I use AB as absolute value of 1 over, I need a dot over because the omega is a vector, right? Denominator is a vector. So 1 plus j times that omega. Okay, so this gives us the first plot. I guess something wrong. Oh, I need one more. Okay, so this is a Fourier transform, the spectrum, right? Absolute value. Here's the absolute value, magnitude. Magnitude of this one, it looks like this. It has a peak value at frequency 0. And when frequency increase to positive side, this one will go to be 0. Right? The magnitude should be go to 0. It makes sense, right? Here's 1 plus j omega. When omega go to infinite, this fraction should go to 0. Right? So it looks like this. One peak in the middle. And then we check the second function, second Fourier transform. This is this is for DTFT of the sample signal, right? For this one, figure. Okay, this is figure 2. the second figure. I want to plot omega is still omega. This is 1 over, not 1 plus. Now it's 1 minus. 1 minus e to the negative t. Okay, I need to choose a t. I use a sample step t. For example, in the first of all, I use t is 1. T is just 1. You can choose different value on t. Now it's a minus e to the negative t and times e to the, I can just plus, right? Plus, right? These two exponential power put together. We just add the power together. So it's a t plus j omega, minus j omega. Negative t minus j omega. Okay, pretty good. I need one more. Too much. Okay, you see? Now this is the second figure. The first one is here. So what happened? You see? Before they take sample, the continuous time signal. This is the Fourier transform in the magnitude side. It is a peak like this, right? One peak in the middle. And this side is after take sample, you perform the DTFT. You have a sequence of like peak values, and the center will be, you see, this is 6 dot something, should be 2 pi. So it is a copy of the original one, but you have a lot of copies. You put them, every copy is centered at 0, 2 pi, negative 2 pi, and so on. If we use more, like here, if I use omega equal to, here's a 10, right? As a negative 10 to positive 10. I use negative 10 to 50. Now we have more omega. Now what will happen? I still need a figure 1. This is figure 1. Okay. Oh, it's not yeah, I changed the omega from negative 10 to 50. The center is still in 0, right? This is a continuous one. Then this one, we have a lot, right? So basically every 2 pi we have a peak. Every 2 pi we have a peak, right? Every 2 pi we have a peak. The center one is in omega equal to 0. Then here should be pi, should be 6 dot something. Then here will be 4 pi. First one is 2 pi. Second one should be 4 pi. 4 pi should be 12 something, right? Then 6 pi. 6 pi is 6 times 3 is 18. 18 and something more, right? So here. So every 2k pi you have a copy of the original one. This is the original signal, the continuous time signal. Its spectrum looks like this. And here are some copies of it. Yeah, this is just that formula, right? That formula. Okay, then let's see, when t is different, what happened? When t is different, what will happen? Here, like figure 2, okay, I go back to the smaller, less t's. I just go 2 pi, alright? I just use, okay, I just go to 4. Negative 4, negative 3 dot, and negative 4 to positive 4. Alright, negative 4 to positive 4. So we only check one period, from negative pi to positive pi. One cycle, alright, one cycle. Then the original one, this is original one, alright. And after take sample, okay, we have this, right? One cycle, just actually pi is here. Maybe I want to see the 0 to pi, sorry. Okay, let's finish this one. If I want to change, I can change later. Now I change the, before here I hold hold on. Then the graph in figure 2 will not be cancelled when I draw no new one. Okay, t is 1, I choose a larger t, what will happen? T is 2. Okay, you see, a larger t, we have this. Larger t, for larger t, we have this. And we use a smaller t. 2 is larger t. I use a 0.2. Smaller t. Oh, smaller t is this one. It's the more sharper one, right? More sharper one, right? So the things like that, you have. Yeah, I explain here. This is original one. Right? Example. Just this example. XC of j omega, the magnitude, it looks like this, right? Looks like this. And then the magnitude of x of e to the j omega, this one where it looks like something like this, right? Something like this. Here's a 2 pi, here's a negative 2 pi, and you will have one more peak here, will be 4 pi. Every 2 pi you have a peak. So you can think like in the middle, here's a negative pi, 2 pi. This part is just like this part. Right? You copy, you do some scale and put it here. Right? And this point, here's omega equal to pi, lowercase omega equal to pi. Then this point is what? This point omega equal to pi. Let's see the formula. It's here. We check the center one. Center one k is 0, right? It is just xc of j omega over t. Now omega is pi, so this is a capital C of j omega, the pi over t. So this point, it is pi over t. Okay. This point is pi over t. This point is negative pi over t. You can think is you take this part and put it here. When t is small, this one will large. So for small t, you will have more part, right? More part from here. When t is small, you have more part from here. You put it here. When t is large, this value will be small. You will use small piece. Put it here. So the information for small t, this part contain more information, right? The whole thing, you change the scale and make it fit this space. Here the space is negative pi to pi. And here's for small t, you have large part. You make it, press it to be fit this one and put it here. All right. Got it? So smaller t, you will have more information will be kept it here. For larger t, then you have less information. And the outside part, you can think they are lost. They are not lost. They'll still be here, but it is covered by next peak. Right? This part will be some small value here. It is covered by this peak, so you can think they are lost. Yeah. All right. Yeah. We can try more. Can we have? Let me see. XC. Which one? This one here. Yeah. This is a signal like this. Can we have a signal more better to explain it? Okay. Anyway, this one is fine. Okay, now let's make the T. This is small, right? It's small. The another side, if I make it large, what will happen? Like 2. Oh, I already have 2. Like 20, even 10 times of it. Now the sample step is very large, 20 as a step. So that means you lost a lot of information. What's that? You see? This curve almost a straight line. The last one, right? This is a t equal to 20. T equal to 20. So the thing is almost a straight line. What happened here right now? You think like this. This is a XC, the continuous one, the original one. And now you use t equal to 20. So you have this part. This will be pi over 20. Pi over 20. And this side is negative pi over 20. And then here, this is a negative pi, this is a pi, this is a lowercase omega. I mean the graph is capital X of e to the j omega, the Fourier transform of the sample of the signal. Now you need to put this part to here, so it looks like almost a straight line, like this, like this. Yeah, so when you have all of this, it looks like just a straight line. Just looks like a straight line. This is a very little bit change. You can see. You only have this. So when you look at it, use your eyes, you think this is straight line. Actually, it is not really straight line. It's just still a curve, but the difference is very small here. You have straight line. Yeah, this is 20. So in this case, you check this one. This one contains the information. You only know this part. Actually, all the rest part will be here, but covered by next peak. Right? It will be things like this, and the next peak will be another one is here. Yeah, peak by peak. Yeah, and this part you can see we have a name. We call this is a kind of overlap. This part is here. It should be longer. Is here. Yeah. So this part is this part. So this is the overlapping. And this is the next peak. Next peak will cover these. Okay, so this is how to take the sample. Oh, I go over like this way. I go this part very fast. Okay, somehow this class is shorter, but this is what do I want to show you today. Can we have more? I have 10 more minutes. So we can have another one. Actually, that one is related with next topic. So far, we consider two things. One thing is when we take sample, what happened in time domain? Right? What happened in time domain when we take sample? This is quite simple. You just take samples, right? From a continuous curve, you have a list of values. You take sample. The second one is what happened in the frequency domain. We perform Fourier transform. Both the signal, original continuous time signal, and the sample, the discrete time signal, we take Fourier transform. Both we take Fourier transform. We have these two. Then what are the relation between these two? Then we have this formula. And this formula, the meaning is things like this. Right? The things look like this. You just original ones look like this, and you put these in the negative pi to pi piece, and copy the center one at each part. Then you have this one, right? Okay, the second thing. And the third thing is we have another signal. That signal will be used when you try to restore the signal. Suppose you have the sample, right? You think like you take sample and you keep the sample in storage. Next time you read your samples, the samples in your disk or in your computer or something, then you have a sequence of date. You want to recover the original analog signal. Now how to do it? To do this restore the original signal, you need another signal. So here we have one more signal. Which will be used to restore XCT from Xn. That is XS of t. XS of t, it is a summation of x of n times dirt of t minus nt, and run from negative to positive infinity. Alright, it is this one. It is a it is a continuous time signal. It is XS of t. But it is not, its value is not continuous. Its values are parts. Like this. You have sample, every sample you have a part, but the peak value is given by xn. Right? You times dirt times x on the dirt. Dirt is a unit impulse, right? You times on the impulse. Use xn times on it. So this is a x1 of dirt. Like this is x1 of dirt, 1, 2, 3, 4. This is x4 times that dirt, and here's the value. The dirt, the parts occur at time t. So here's the t, n of t, 1 of t, 2 of t, 3 of t, 4 of t, things like that. So what happened here is we take sample. When we take sample, this one. When we take sample, original one, it is a curve. This is a signal in time domain. It is a curve. Then we take sample. We have sequence of values. Now we have another signal. This one. We have this one. Put them together. Put it here. Alright, I put it here. Okay. This one we take sample, we get these. But this is just some list of values. I use this graph to represent it, but exactly we only have this list of values. We do not have anything between them. Now we build another signal. This signal, between these parts, its value are zeros. It is not nothing. There are values. There are some values here. These values are zero, but they are not nothing. They are something here. They are zeros. So we have this xs of t. It has value for any t. Just looks like this. 0, 0, 0, 0. Okay, a parse. Then 0, 0, 0, a parse. 0, 0, a parse. 0, 0, a parse. It is different with this x of n. Xn just a value, just like that. Between two values here, nothing. Not zero. Here's nothing. Alright, no value. Here's a value. Value 0, but they are values. Alright, this is xs of t. So this is a continuous time signal. This is analog signal. This is discrete time signal. Okay, for this xs, we perform CTFT. We already have this one is 1 over t times summation of xc of j omega minus 2k pi over t. We have this formula, another formula. This is xs of j omega equal to this one. So we have a formula like this. The next time I will use this one to restore the original signal. This one you can think about it, what it is. This is some summation of some xc. Each is a xc shifted by 2k pi over t. So this time the graph will looks like this. I still use this one. Suppose this is a magnitude of magnitude of xc looks like this, like this, and then this one's xs of j omega. This is xs j omega. It is this one. It's a summation of this one. So it looks like you have same, exactly same. Here no scale on omega, no scale on omega. You have out of this, but the center here is 2k pi over t. So the first one is 2 pi over t, and if you have more, the third one, the first one, second one, this is the third one should be 4 pi over t. The negative side, this will be negative 2 pi over t. Center is here. And this point is pi over t. You can think here's the same scale, pi over t, negative pi over t. So you can think this part is here. Same scale. You can compare with this one. Compare with this one. X of e to the j omega. You put this part to negative pi, between negative pi to positive pi. You need to do some scale. Maybe you need to push it, make it narrow, or pull it, make it wider to put it here. And this one is still from negative pi over t to positive pi over t. Still this part. But this part, put it here, just directly put it here. No scale. Just put it as same as this. You put it here. Then next, you put it here. Then one more, you put it here. You put them together. All right. Yeah. Okay. That's all for today. And I have some homework problems, just a few problems about the sampling process. You can check the Blackboard. This homework will be due next Monday. All right. We go back to the normal time schedule after the exam. Yeah, time is shorter, but problem is only few problems. This homework. All right. Okay, see you next time, and have a good weekend. Bye bye.